Hello, good morning everyone. My name is Krzysztof Puławka and I am a researcher in the rock engineering department of KGHM Cuprum. At the beginning, I would like to thank you all for your presence on today's webinar. During today's presentation, I will discuss the issue of modeling of large-scale underground mining structures under static load conditions. Here you can see the agenda of the presentation. I will start with the introduction of KGHM Cuprum Company and the description of the Baltic Sea Underground Innovation Network project. Then, information room and pillar mining system and seismic activity in the Legnica-Głogów copper basin. This is the southwest of Poland. After that, I will describe the issue of numerical modeling in mining and, of course, facing the ground control problems. Then I will show you the whole process of model preparation in FEM based GTS NX software. And finally, I will show you the results of numerical modeling of the conceptual trial panel for R&D purposes under static load conditions. So, maybe a few words of introduction of the KGHM Cuprum company. We are R&D center focused on the development of new technologies and methods for both underground and open pit mines. At the moment, we provide the projects and solutions for the mining industry in 31 countries, and we offer expertise and research works, design, measurement, and laboratory services. We are also experienced in the ground consulting and normalization services. I need to highlight that KGHM Cuprum has over 50 years of experience in supporting of Polish and international mining industry, and I believe that this is the best reference for our quality. At the Rock Engineering Department, we offer a range of services from in situ measurement through risk analysis and assessment to numerical models and recommendations for safe operation and development of new innovative mining solutions. My team has a great experience in the implementation of solutions aimed at evaluating of the effectiveness of the mining process and continuous long-term monitoring of stresses, inclination, and seismic activity as well. What is worth mentioning is the fact that our solutions are always verified at the site, and therefore it always fulfills our clients' requirements. Of course, apart from underground measurements, we carry out numerous research tasks aimed at the estimation of the levels of geomechanical hazard, risk prediction, and adjusting of the optimal monitoring solution to the local mining and geologic condition. Moreover, one of the main tasks performed by the rock engineering department is the numerical modeling of the stability of the geotechnical objects and underground workings in static and dynamic load system. In recent years, we have also specialized in designing of active rock burst prevention using numerical tools and analyzing of floods and waste flows as the result of failure of large dams and tailing storage facilities. In the case of underground mining, numerical models are most often used to evaluate the impact of mining works on a general state of geomechanical hazard. This issue is highly complicated mainly due to great dimensions of the numerical models and constantly changing values of the strength parameters of the rocks. Of course, this variability is related to the process of continuous disintegration of the rock along with the progress of mining works. Still, in today's meeting I will present you a kind of case study. We will discuss the process of preparing of large-scale numerical model of underground laboratory, which could be potentially located in the workings of Polkowice-Śroszowice mine. This is the deep underground copper mine in Poland. And the feasibility study was prepared based as a part of Baltic Sea Underground Innovation Network project. The results of the task carried out by KGHM Cuprum was a large-scale model of mining panel prepared with the use of room and pillar mining method. In order to bring you closer to the challenges related to the design of room and pillar mining systems, a few words of introduction in the field of the development of this kind of exploitation method. The room and pillar mining system is one of the oldest methods of underground mining, mostly of deposits located in the hard rocks. Initially, the exploitation was carried out with the non-systematic manner. I mean that the size of the pillars were selected empirically, and for example, the access ramps and the sidewalks were laid in the most convenient way. Here on this slide you can see the sample map of workings in the coal mine. This was the George Creek Big Queen in Maryland from 1850. As you can see, the geometry of the workings were sort of chaotic, and unfortunately such way of exploitation led to the moment when pillars of or dimensions of pillars were too small, and often led to the compression and crushing by the overlying roof layers. As a result of such situation, a specific chain reaction occurred, and unfortunately it was very difficult to control and most often resulted in destruction of significant part of the mine. Based on the experience gained in the past, steps were taken to standardize the technological parameters of the room and pillar mining system in such way that allow to adapt it to the specific condition of the deposit. Of course, system began to be planned in such way that allowed for achieving compromise between safety and production rates. Along with the development of knowledge on the subject of behavior of the rock mass disturbed by mining operations, the size of rooms and pillars began to be selected based on the number of calculations. Of course, the geometry of single pillar was dependent on the load which was generated by overlying strata and the load-bearing capacity of the material located in the pillars. In addition, in order to prevent the formation of large-scale failures, the deposit was divided into smaller mining fields, mining panels, between which large-sized pillars with geometry much larger than in the case of technological pillars were placed. It made it, of course, possible to limit the development of potential instability to the area of one mining panel. Maybe now I will show you very briefly how room and pillar mining systems evolved in the case of Polish copper mines and what kind of impact it had on the safety of exploitation. In the first years of exploitation in KGHM, two-stage room and pillar mining systems were used. In two-stage systems, the exploitation field, exploitation mining panel, was cut with rooms in such way that allowed to achieve large-size pillars, which was supposed to support the roof layers. This was the stage number one. Then, these pillars in the second stage of exploitation were cut with rooms, what allow us to create technological pillars, which can work in the post-critical phase. This was the stage number two. Unfortunately, the two-stage systems, two-stage room and pillars mining systems, due to the large dimensions of the pillars cut in the first stage, contributed to an increase of seismic activity in the exploitation field and at the same time increased the geomechanical hazard within the working area. Based on the experience gathered, it was found that due to the concentration of extraction and high risk of the rock burst, one-stage systems should be more advantageous. In one-stage systems, technological pillars were cut to the target dimensions in the first phase, without prior cutting into large size pillars. In the case of the deposit of medium thickness, I mean in range of 3 to 5 meters, one-stage systems with the roof collapse were most often used. The roof collapse goal was to fill the exploitation void with the rocks which fell from the roof. This is supposed to be a sort of backfilling of the working. What is important is the fact that roof collapse was forced by detonation of the explosive charges placed in the long blast holes in the roof. Of course, the blasts were carried out in the distance of about 30-40 meters, and the length of the blast holes was about 10 to 12 meters. As it turned out later, the volume of the blasted rock with this method was too small to fill the void, what in effect made it impossible to sufficiently support the roof layers. This in turn translated into increase of the rock mass pressure on the mining front, and finally increase the frequency of the roof collapses, what of course affects negatively on the economy of the deposit exploitation. Therefore, in order to slow down the process of filling the post-exploitation void and reduce the geomechanical hazard, one-stage room and pillar mining system with roof deflection has been developed and implemented to regular exploitation. In such type of systems, liquidation or maybe backfilling of workings was done by cutting of pillars to such dimensions which allow roof layers to achieve the partial steady deflection. The effect of implementing such systems with roof deflection was not only significant increase in the safety of the crew and machines, resulting of course from the reduction of the number of collapses, but also significant improvement of economical results of whole exploitation process. There is also room and pillar mining system for the deposits with a thickness of more than 5 meters. This is a two-stage room and pillar mining system with a hydraulic backfilling. In the first stage, the field was cut with rooms and pillars into the geometry of 25 per 25 meters. In the second stage, large size pillars were cut with 6 meters wide rooms, and after selecting of 3 adjacent chambers, the 3 1 meters wide barriers were created. These barriers were located next to each other, and backfilling dams were built, fencing off the Gulf zone. Then, after the separation of this space was filled with the hydraulic backfilling. Of course, the systems that I have presented to you are used in many varieties, adapted to the local geological and mining conditions. Currently, the catalog of operating systems describes about 20 variants of systems that are still in use in KGHM mines. Getting to the point, a few words of explanation. Why did I describe here the evolution of exploitation systems? Basically for 3 reasons. Firstly, to show that the appropriate planning of geologic works in relation to the local geology and mining conditions gives tangible benefits in form of minimizing the geomechanical hazard. Of course, confirmation of these words can be, for example, observed in these graphs, which shows the distribution of seismic activity in KGHM mines over the last 30 years. As you can see, modifications of the method of selection of the deposit, which I briefly discussed today, translated into the clear decrease in seismic activity recorded in the following years. Secondly, I would like to point out that despite the clear effectiveness of the actions undertaken, based on the simple analytical calculations and the experience of the mine staff, the whole process of minimizing the seismic hazard by modifying all the methods of selecting was extended over the period of several years. From the point of view of economic results and accident rates, this situation is very unfavorable. Because we would like rather to have the results during the few months, maybe few years, but not dozens of years. The third thing is the level of activity, which has stabilized since 2007, but still remains at a high level. This could mean two things. First, the methods which are currently in use are already optimal and there is no way to further minimizing of seismic activity. Or second, in my opinion, more likely, the possibility of methods based strictly on the experience of the mine management have already run out. And this is necessary to implement new, more advanced calculation methods to regular use. And here we come to the main subject of today's presentation, I mean numerical modeling in mining. It just so happens that despite the fact that modeling tools have been available for many years, in mining practice they are not used regularly for design of mining work, for example. Analysis, any kind of analysis, for example, using the finite element method, are used rather in certain special cases, for example, to analyze the causes of very serious accidents or to analyze the geomechanical risk in the areas characterized by, any disturbance, any geological disturbance, or maybe some presence of key infrastructure, etc. But in standard regular mining planning, the numerical methods are not commonly in use. Nevertheless, when analyzing the current literature on the subject, it can be unequivocally stated that numerical simulations are becoming more and more important in the case of issues related to the risk assessment and mining industry design. In this slide you can see the general breakdown of numerical methods applied in mining, including underground workings and surface-based objects. And as you can see, when assessing the stability of geotechnical objects, the most common method is the simplified LEM method, limit equilibrium method. But we use also the more advanced methods like FEM and FDM methods. Importantly, the use of FEM and FDM methods allow to perform calculations in dynamic load system, which is currently not possible with use of LEM. In the case of underground workings, the LEM method is rather not used. In this case, the methods enabling the performance of dynamic calculations and taking into account the large variability of geology and rock performance parameters, rock strength parameters such as DM, FDM and FEM become more important. The FEM and FDM methods are also applicable in the case of stability calculations of the mining infrastructure, which is exposed to the occurrence of large deformations or maybe on the influence of the seismic wave interaction. Dynamic calculations in FDM and FEM methods are also useful for all types of calculations related to the design of blasting works or the assessment of the seismic effect generated by this blasting work. Of course, you have to bear in mind that these methods I have listed are only a few of the many available on the market. But as our experience in this area shows, at the moment such method seems to be the best validated and allow to the best possible representation of the reality. And now, as part of this webinar, I would like to present you the possibility of using numerical finite element modeling using GTS NX software to estimate the risk associated with maintaining the stability of underground workings. Unfortunately, problems with maintaining the stability are local phenomena resulting from the geological structure of the deposit, especially in the vicinity of the workings of the mining area, the exploitation system which is utilized, and the used mining support. All these parameters have really significant influence on the risk level and of course affects the possibility of instability occurrence. Unfortunately, as recent experiences showed, problems with maintaining stability have a very strong impact on the general state of safety and accident statistics in KGHM mines. Therefore, we are doing everything to be able to counteract these events. However, in order to be able to prevent these events, we must first estimate the risk of their occurrence. And here it is necessary to indicate that application of the tools for FEM of FEM based numerical modeling allows to estimate the stability of workings before starting of mining works. So it remains to decide whether we want to perform our analysis in two-dimensional or maybe three-dimensional environment. Now please take a look at why I believe that modeling of room and pillar mining systems should always be performed in 3 dimensions. In this slide you can see the comparison of results of 2D and 3D numerical modeling of tunnels excavated in intact rock. If it is not necessary to take into account the changes of geometry and variability of trench parameters in the vicinity of the excavation, it can be actually stated that results from 2D and 3D analysis converge with each other very well. Here we compare the results of calculations which were made for a few variants of tunnels excavated in various types of rocks with different cross-section shapes. And indeed, according to the results, if material is homogeneous and the excavation is performed in one direction without visible changes in the geometry of workings, then the two-dimensional models will reflect enough the actual situation in the surrounding of analyzed area. In turn, if there is any variation in trench parameters within the entire model, then unfortunately modeling in 2D leads to incorrect results and should not be used for analysis of this type. Please note here two examples of 3D modeling. On the left you can see the results of modeling of the stability of the edge at the edge of the pillar, where the possibility of the ejection of the rock block from the pillar under the pressure of the overlying layers, depending on the depth of the workings, was analyzed. Using 2D modeling, we would always have to assume that the excavation has a tunnel character, and it is not possible to design rock ejection into the analysis. Of course, the ejection from the corner of the pillars. In addition, if we take into account any kind of variability or non-linearity of geometry within the model, we can observe that the layout of excavations affects significantly the stress distribution. Even assuming the same strength parameters of rocks in the vicinity of the model, of course the pillars located closer to the mining front or at the edge of the mining panel will be loaded more significantly than pillars located within the existing workings. This, of course, corresponds to the real situation in underground area. So, moving to the model, which is the subject of this presentation, I would like to show you the entire process of preparing the large size model from geometry through meshing and selection of strength parameters, to the results of the analysis, which will be basis for decision whether a given project can be implemented in this form, or maybe it is necessary to make some modifications in the project. In the first stage, it was necessary to prepare the site plan of the excavation, and of course design place where it is planned to place underground laboratory. This laboratory, as I said, was intended or supposed to be placed for R&D purposes. The general assumption was that the laboratory, for technical reasons, was planned to be located in about 1.2 km from nearby SW1 ventilation shaft. It is one of the main ventilation shafts of Polkowice-Sieroszowice mine, and please pay attention to the colors in the presented situation plan. The workings that have already been excavated but have not been liquidated yet are marked blue. This means that these workings are still available for transport, ventilation, etc. The backfilling areas are marked green, and as you can see in the vicinity of the shaft, some of the mining fields were backfilled with the use of hydraulic or dry backfilling. Of course, this was to increase the geomechanical safety of this area. Moving forward, brown area is the area which represents the intact rock mass, so rock mass which has not been excavated yet. And finally, the underground laboratory project was marked with pink color. Generally, the length of the workings planned to be excavated for the construction of this laboratory is about 9 kilometers, so quite big project. Of course, due to the fact that designed mining panel was not supposed to be excavation panel, it was necessary to take into account that we have to maintain the designed excavation for longer period of time. Of course, we need to ensure the stability for few or even several years. Therefore, the designed dimensions of the pillar were much larger than the standard pillars used within the exploitation mining panels. The designed width of the pillars was about 15 meters, while the length of the pillars was about 30 meters. Additionally, within the designed operating mining panel for R&D purposes, 8 special purpose chambers were designed. And these chambers were prepared for the purposes of machinery chambers, chambers for scientific equipment and material storage, or mining chambers where the crew can stay in the period between shifts. These 8 chambers had larger dimensions and therefore single chamber was about 6 to 10 meters width, 15 to 20 meters long, and 6 to 9 meters high. Okay, so when the geometry of the excavations located at the deposit level was ready, it was necessary to prepare the geological model of the layers located above and below the plant mining panel. For this purpose, I recommend using the bedding plane tool, which is available in the GTS NX software. This tool allows us for mapping the real geological system of layers based on the data from exploration drill holes, for example. And this is a very simple and quick way for preparation of geology for the model. In the case of our model, we use the data from 4 boreholes. Here I would like to mention also that the bedding plane tool, although very easy to use, greatly facilitates the modeling process and increases the accuracy of the simulation. Of course, accuracy increases with the increasing number of boreholes, but still, in our case, 4 boreholes were totally enough. I would like to also emphasize the fact of large dimensions of our model. This cuboid presented on this slide have dimensions in the x and y direction of 2 per 2 kilometers, while the z component, I mean depth, is about 1.5 kilometers. Therefore, the standard model of underground mining in static load system has volume of about few cubic kilometers. So this is really big model. And what is worth mentioning is the fact that using of GTS software guarantees the possibility of stable calculation even of such large models. The next stage of our numerical modeling is the selection of appropriate rock strength parameters. The question is always the same: whether we should use data from laboratory tests or maybe try to reduce the strength of the rocks on basis of various analytical formulations. In general, this problem is very complex and complicates the entire modeling process, but some assumptions, of course, have to be made. I think that the words said by Kazimierz Puławski are good reflection of this issue. He said that what causes problem for us are not the things we do not know, but the things we are sure we know perfectly well. However, in this case, in the case of geomechanical analysis, it is better to slightly underestimate the strength parameters of rock than overestimate them. Therefore, when preparing data for numerical models, we use so-called rock mass classifications. And there are, of course, several types of rock mass classification. But I believe that rock mass classification proposed by HEC, I mean GSI classification, is one of most popular and probably most accurate one. So this is one which we use during our modeling. Here you can see some examples of the GSI values depending on the level of the rock disintegration. This method is based on the qualitative assessment. And now, depending on the degree of the fracture of the material, the appropriate GSE level is selected. Of course, this GSE number is used then to calculate or maybe reduce the parameters describing the strength of the rocks. And for example, it is possible to reduce the deformation modulus in accordance with the relationships which is presented in this slide by using the GSI value. And then we need also to know the value of uniaxial compressive strength, which is result from laboratory tests, and then we can calculate the reduced modulus of deformation. This approach is very simplified, but it is well suited to FEM calculations. Of course, the GTS NX software allows you to simulate the cracks within the model, so you can do this in both ways. You can reduce strength parameters with GSE scale or simulate cracks within the model. But in our case, with the geometry at the level of several cubic kilometers, introducing the cracks network to the numerical model or the network of joints to the numerical model would significantly extend the calculation process, calculation time, and would involve the need of engage much more powerful hardware resources. And here you can see examples of changes in the angle of internal friction and deformation modulus depending on the selected GSI value. Of course, the reference level in the GSI scale is 100 points, which corresponds to the strength of intact rock resulting from laboratory test. And now the reduction of the GSI value makes it possible to read the values of the angle of internal friction and the deformation modulus from the graph. So you can check there what level of angle of internal friction or deformation modulus will correspond with your GSI level. Another step or another element of the numerical modeling is the selection of an appropriate strength hypothesis. In the analyzed case, we applied the elastic plastic model using the Moore-Coulomb strength hypothesis. Generally speaking, in the static load system, this strength criterion allows for good reflection of the actual situation within the rock mass. We verified this many times with use of underground measurements in situ conditions, and our research proved that Moore-Coulomb model, Moore-Coulomb criteria fits very well our deposit in static conditions. Nevertheless, I would like to point out that according to our experience, in the case of modeling the stability of objects, underground objects in the dynamic load system, unfortunately the Moore-Coulomb strength criterion seems to lead to incorrect results, but still this is not the subject of this presentation. In the static load system, I need to highlight it one more time. The Moore-Coulomb criterion is one of the most credible approaches. Okay, but I have also to point out that due to the need to present our results or results of modeling to the customers, we always try to define the safety factor distribution. The GTS NX software, of course, enables determination of the safety factor for entire area of the model. And of course, interpretation of the safety factor is very simple. Values below 1 may indicate the probability of instability occurrence, while values above 1 should guarantee the stability of the excavations. Moving on, here you can see the GSI values that were adopted for the preparation of the model. In the case of an intact rock or non-cracked rock mass, the GSI value was assumed at the level of 80 points. In turn, in case of the zones which are directly located in the surrounding of the excavation and in all technological pillars, the GSI value was at the level of 40 up to 60, depends on the area which we analyzed. At the same time, in the case of liquidation zones, the GSI scale was not used. In this case, we used the loose sands, loose materials, and fill all areas of backfilling with such material like sands and gravels. So safety factor of these zones should be equal to 0, but still it should generate some kind of support for above located roof layers. And last, but of course not least, I think this is the one of key elements of the entire process of preparation of the numerical model. I mean generation of the mesh. For practical reasons, we cannot use the same size of the mesh for entire model, because such approach would involve the generation of several billions of finite elements, so it will be too much, definitely. In this case, it is necessary to increase the size of element while keeping in mind the necessity to use the mesh dense enough to make calculation results reliable. And of course, we have verified the optimal size of the mesh at the level of the mining panels on the basis of trial models. As our calculations show, as you can see on this slide, it is optimal to use elements with size of about 1 meter. And in the figure on the bottom of this slide, you can see the calculated values of the safety factor for pillars, which were made of elements with size of 0.25 to 25 meters in the center of the slide, 1 meter, and 3.5 meters. As you can see, the differences between 0.25 and 1 meter are invisible, while when we increase the size of elements up to 3.5 meter, we can observe the significant deterioration of the results. Still, I would like to highlight that GTS NX software has a very efficient and accurate mesh generator. And thanks to this generator, it is possible to prepare the first version of the mesh in automatic mode, which is very important in case of room and pillar mining model preparation. And of course, after preparation of automatic mesh, we need to correct it or clean it manually. We need to check if elements have correct angles and dimensions, etc. But still, this automatic mesh generator is very accurate and it is very helpful at the first stage of model preparation. Additionally, a useful function of GTS NX software is the possibility of using a hybrid mesh. I mean that in most cases at the deposit level we use a mesh of triangular shape. So triangles rather were verified to be stable during the calculation of very big models, so we use them in standard way. But if we move away from the designed working level, so if we go below the mining level or above, we increase the size of elements and switch to the hybrid mesh mode. And this action allows us to significantly reduce the number of elements in our model. And as you can see in this slide, in extreme cases, the size of elements increase from several dozen of centimeters within the deposit level up to about 100 meters on the near the ground surface. And finally, the model that which we have prepared within the part of the Baltic Sea Underground Innovation Network project included about 4.7 million of finite elements. So it was a relatively large model, but GTS NX software does not have a problem with calculation of the model with such big size, as long as the mesh and model are well prepared and cleaned of any element that could badly affect the stability of the solution. And now I would like to briefly discuss the results of our analysis. First thing which I would like to show is the distribution of the shear stresses. Shear stresses are an element that until recently was ignored because we most often focus on the axial stresses within the area of excavation, the value of which largely determines the effectiveness of used as excavation support. So we analyze the axial stresses to determine what stresses we can observe in the surrounding of the workings and what support should we use to to provide the stability of the workings. But as mining practice show, especially in the recent years, shear stresses may appear in some areas of the mine and are particularly harmful because of both the strength of the rocks and the strength of the rock wall support used in KGHM are relatively low in the case of the shear strength and compared to axial strength. And now, in fact, there is no available roof support system that would enable effective protection against these shear stresses. So we need to use rather the technological measures in this regard. For example, we can choose the different geometry of the excavation or choose different direction of exploitation. But nevertheless, for technical reasons related to the operating system which is used in our mines, high values of shear stresses might appear, especially in some areas of the model. And the location of these stresses allow us to take appropriate preventive measures to relieve, for example, to provide some relief blasting, etc. And of course, in extreme cases, you can exclude chosen workings from the use. And we can see that the highest values of shear stresses may be observed at the direct vicinity of the mining front, and in the level of in the area of backfilling. So these results of modeling in general fit the situation which we observe in underground in real. Another parameter that can be analyzed based on the results of numerical modeling is the location of areas where we can expect the pillars to be pressed into the floor layers. In the case of the copper ore deposit in the Legnica-Głogów copper basin, the floor layers are mainly composed of sandstone layers. Of course, this sandstone strata is relatively soft in comparison to carbonate layers which lay in the roof of our deposits. So now, when analyzing the distribution of safety factor within the floor levels in the vicinity of our workings, we can observe in which areas of the model we can actually expect the pillars to be pressed into the floor layers. Generally, as you can see in this model, within the analyzed excavation, there is no significant areas where the pillars will actually be pressed into the floor, so the floor will be yielded. Of course, near the gulf, there is an area of concentration of low safety factor values, and of course on the contours of the projected mining panel. However, this level is not such low to indicate the potential threat. This situation is in generally consistent with the observation performed in situ conditions. Okay, and now going further, knowing that the floor layers should withstand the pressure of the pillars, of course with the design geometry, we can proceed to the stability analysis of the pillars within the analyzed area. In the case of the projected mining panel intended for R&D purposes, safety factor values were at the high level, exceeding in all cases the level of 2. So we did not observe any areas of instability in case of projected mining panel. However, it is worth paying attention to the pillars located between two areas of backfilling. As you can see in this slide, the backfill areas, within the backfill areas, the safety factor reached the value of 0, which proves that this area is completely yielded. On the other hand, some of the technological pillars between the backfilling areas are characterized by safety factor lower than 1, which indicates the probability of the failure. With this knowledge, you can take the preventive measures, such as, for example, installing the additional hydraulic roof support at intersections between these pillars, or design pillars with larger geometry, of course, if you are at the stage of projecting of underground excavation. And here you can see the values of the safety factor calculated for the roof layers, exactly 25 centimeters above the mining level. As you can see, the roof above the existing workings and projected mining panel are characterized by values of the safety factor most often exceeding the level of 1.25. At the observed areas of instability are present only in the area of backfilling. In turn, the areas of very high safety factor can be observed above the area of intact rock mass, which the results of this calculation is in general consistent with the underground observations. Okay, so now at the end of the presentation, I would like to briefly present you the results of the preliminary analysis concerning the distribution of the pressure zone in the vicinity of the mining front. Maybe a few words of introduction about the pressure zone. And this zone is the zone of concentration of high stresses in the head of our mining front. Generally, development of mining excavation disturbs the primary stress condition within the rock mass. And of course, it induces changes of these stresses in the surrounding of the excavation, and these stresses accumulate mainly in the area close to ahead of mining front. Therefore, the safety of miners working in this area is associated with the highest level of the risk. Of course, the maximum stresses are observed at the certain distance from the mining front, and this distance is not very well recognized in most cases. Still, we know that this zone exists, and from the point of view of safety, we want to do everything to move this zone far away from the mining front. Of course, move it away as far as possible. And for this purpose, the so-called active rockburst prevention is used. And this active rockburst prevention includes, for example, the multi-phase distress blasting or torpedo blasting in the roof. And the base assumption is that if blasting is effective, then rocks in the zone of increased stresses crack, and the danger zone moves deeper into the rock mass. Of course, it affects the geotechnical threat, which decrease in the result of these actions. And again, numerical modeling with the use of GTS NX software can play an important role in the process of minimizing the geomechanical risk in the vicinity of the exploitation fronts. If the excavations of the rock mass are modeled with the use of appropriately dense mesh, then it is possible to determine the distribution of the pressure zone in the vicinity of the excavation, and of course to determine the potential location of the maximal stress that we want to target by or with our distress blasting. This is a very perspective topic on which we have focused recently, but in this case we have to perform dynamic analysis also, and we have to look deeper into the problem with in more detailed way. Still, based on the preliminary analysis, we believe that it is possible. This is potentially one of the ways to increase the effectiveness of our distress blasting, and of course, finally, we will be able to increase the safety in underground conditions near the mining front. Okay, so summarizing a few conclusions of this presentation of results of our project. The use of three-dimensional numerical modeling in static load system using the finite element method significantly affects the possibility of supporting the design of underground mining, and of course increase the accuracy of geotechnical analysis and the risk assessment. Of course, the determination of parameters such as the safety factor, stress distribution, pressure zone range, as well as the location of the overloaded zones is the basis for rational planning of the geometry of the excavation, selection of the rock ball support type, and of course designing of the distress blasting work, which are the basic element of the rock burst prevention in the Legnica Kłodzków-Koper basin region, in KGHM mines in general. The use of the GTS NX software for modeling of above mentioned conditions it enables the preparation of large size models with dimensions of several cubic kilometers, which is crucial from the point of view of geomechanics and stability analysis of workings in room and pillar mining systems. As you can see, numerical modeling performed for the purposes of the geomechanical analysis is gaining importance, and I hope that over the next few years numerical methods will not only be addition to the mining design process, but rather be a regular part of the entire mining planning process and periodic risk assessment. From my side, this is all. Thank you very much for your attention. If you have any questions, please send them here in the chat in the GoToWebinar application. Additionally, if someone was unable to attend this live webinar and watch the presentation from the video, please contact me directly if you have any questions. Here you can see my email address and telephone number, so feel free to contact me. Thanks again for your presence, and goodbye.